All right. So this chapter is all about amino acids, peptides, and proteins. So, complete like off the bat, just, this is going to be a really long chapter. There's a lot of stuff you guys need to both memorize and understand. Um, I promise you, things that you have to understand are incredibly conceptually complex. Like much is in 109C, we focus a lot more on a lot of honestly memorizations than conceptually based things. There's a lot less reaction mechanisms and more of just like a general understanding of like, okay, what are some important structures in biochemistry? Like, what are some important techniques that we use, whatnot. But with that, let's just get right into it. Okay, amino acids and peptides. So, an amino acid is something of the form where we have a carbonyl and directly attached to it, we have an OH, so carboxylic acid and we have an NH3 that's connected alpha to um, the carbon, like carboxylic acid. So we have an alpha amino carboxylic acid, right? Amino group. This is the alpha carbon connected to the carboxylic acid. And we have this R. This R is the side chain. It's the thing that's variable. Okay. So in all amino acids, they'll have this structure, except this R will be variable. The one caveat to that is proline. And when we get to that, we'll see like why that's the case, right? So amino acids are linked together by amide bonds. Okay. So all this is saying is N next to a carbonyl O, it's an amide bond, right? And we get that same pattern of, like we have the same general structure for all the amino acids and R, R, R. So I would get really comfortable with learning how to draw it in this structure and then just writing the R's like this. Okay, proteins, these range from 40 to 4,000 amino acids. Fibrous proteins are long fibers that are insoluble in water. Structural proteins are examples. Globular proteins are proteins that are roughly spherical in shape, soluble in water. Almost all enzymes are globular proteins. In terms of nomenclature and structures of amino acids, there's about 20 naturally occurring amino acids that you're on the hook for. I don't know to what extent you need to know the structures, names, and abbreviations, but I think you're on the hook for all of it. But that's a little Quizlet. Get down the structures, get down the names, get down the abbreviations. And I mean, this really is the language of biochemistry. So, in all future courses, they will be reliant on understanding of this, at least for 108A. I think it's just a good thing to know and a good thing to have a general understanding for going forward, though. But anyway, stereochemistry of amino acids. A D sugar is when we have this OH on the right side. D amino acid is when we have the NH3 on the right side, L amino acid, NH3 on the left side, right? So this is the Fisher projection. Um, again, so alpha carbons of all L amino acids have S configuration except cysteine. Um, Cysteine's difference is because we have cysteine as a sulfur-containing compound, and when we get to cysteine, I'll point out like, okay, like this is why we have a different configuration. This is why we actually have R. But yeah, just keep that in mind. It's a really easy thing to test on. Cysteine being the only thing that has R configuration. All right, acid-base chemistry. So Henderson-Hasselbalch says pKa is equal to pH plus log of HA over A minus. We've seen this equation written 13.4 billion different ways, right? And, it's good to have an understanding of manipulating this equation into different forms and log properties, right? This becomes a minus if we switch these. We can move this to the opposite sides. The way that I usually like to write is pH is equal to pKa plus log of A minus over HA. But, you know, it does vary. The idea though here is that we have these amino acids, right? Carboxylic acids and amines are the two groups, right? And at different pHs, they have different charge values, right? You can see at a pH of 0, the pKa is 5 of a carboxylic acid, right? So 5 is equal to 0 plus log of some number. And we know this number must be really positive, right? Because 5 is equal to 0 plus log of this whole expression must be equal to some really large number. So we know that HA is 10 raised to the 5 times more than A minus. So this is the predominating structure. At pH of 7, we see that we have pKa of 5 equals 7. So minus 2 is equal to log of HA over A minus. So we clearly favor the bottom thing, the denominator, because it's negative, right? So we know that we favor this structure at pH of 14. We favor the structure even more. We go through the same process of amines, except their pKa's obviously being protonated pK or protonated amines are pKa of 10 to 11. Um, cool. Um, Amino acids, right? So all we're doing is we're looking at these functional groups, we're putting them together. So when we look at the net charge, we know that the net charge goes from plus to zero to minus, okay? And this zero isn't precisely at pH 7, always. Sometimes it could be, but not necessarily, generally not. But we'll get into that in a second about what PI means or, like what it means to have a net charge of zero. But the idea here is like, you can see a net charge of +1 in the structure because this amine is positively charged and this is not. We can see a net charge of zero because we have a minus and a plus that cancel each other out. And we have a -1 because we don't have a charge here and we have a minus charge here. So what ion is a compound with a positive and negative charge that are on non-adjacent atoms, right? So here we can look at the isoelectric point, the pH at which there's no net charge on the amino acid, which generally is Zwitter ion, right? So the way we can find out the PI, the place at which the net charge is zero, is by averaging the pKa values, okay? And this works tremendously well and is really easy to do when we only have two groups that have relevant pKa's. But it gets a little bit harder to do when we have more ionizable groups. Like you could see here how like okay, the general structure only has two things that will vary, right? The carboxylic acid and the amine. But for some amino acids, we have functional groups that can also contain a charge, right? So we have to take that into consideration. Um, and we'll get to that when we get to that, right? But for this, the pKa here is 2.32, the pKa here is 9.62, and they're, like I said earlier, the pKa of a carboxylic acid was 5. And that's just a carboxylic acid in isolation, right? So putting this on this structure changes the precise pKa, right? The same way a protonated pKa of an amine is like 10 to 11, it's 9.62 on the specific structure. Just keep that in mind. Resonance and all the sterics and all the other effects make it so that we have 2.32, 9.62. And the pKa's are the points where we like go from one structure that's not predominant to one that is, right? Because pKa is when we have the same amount of acid as we do base, right? So neither of the structures are predominant structures, but the second we go above this or below this value, now Henderson-Hausbach says, okay, like when pKa is equal to pH, this term is zero, right? 1 to 1. But when it's greater, we have more HA. When it's less, we have more A minus. So then we know the predominant structures, right? Okay, cool. So let's look at lysine. So lysine is an example of when we have multiple groups that are charged or non-charged, right? We have multiple groups that can change their charge based on changing a pH, okay? So here we have another amine, a protonated amine. The pKa is slightly different than this because of, the nature of where it's placed in the structure, right? And it's more in line with the 10 to 11 we were expecting because it's so far away from these functional groups, right? We kind of saw with dicarboxylic acids in the previous order that the further apart the functional groups are, the less of an effect they have on each other, which, intuitively makes sense, right? So these are the states at which we change charge, right? And we'll find that the PI is zero between here and here. So we average these two pKa's. Generally speaking, for amino acids, you just average the pKa's that are closest to each other. So 8.95 is a hell of a lot closer to 10.37 than 2.18 is, right? So we average those two values. Okay, amino acid structures. So glycine, alanine, valine, leucine, isoleucine. These are the aliphatic side chains. They're the ones that are hydrophobic. So they're the ones that are generally folded into the interior of a protein when we're in an aqueous environment. Recall that nonpolar favors nonpolar, polar favors polar, right? So since these are the nonpolar amino acids, we want to minimize their interactions with an aqueous solvent, i.e. like water or, salt, which is why they'll be on the inside, right? This is the hydrophobic effect. This is just like dissolves like. It's not too important that you know the precise meanings and definitions as long as you understand the general concept of what's going on here. These are the names, these are the abbreviations. You have to memorize these. There's really no easy way to it. You just have to draw the structures a bunch of times until it kind of clicks, right? Okay, hydroxy-containing side chains, serine, threonine, sulfur-containing side chains, cysteine, methionine. Cool. Okay. Amino acid structures. These are the acidic side chains, aspartate, glutamate. These are the ones that are negatively charged, negatively charged. Amide side chains, asparagine, glutamine. Basic side chains, lysine, arginine. So I misspoke here. These aren't necessarily the ones that are negatively charged. These are the ones that are generally considered to be negatively charged because they're basic side chains, right? And we'll go over acidic side chains a little bit later on. Amino acid structures, benzene containing side chains, phenylalanine, tyrosine, heterocyclic side chains, histidine, tryptophan, proline. Cool. And like I was saying earlier, proline is the only one that doesn't have the exact structure because it really is the same structure in that we have a carboxylic acid and then we have an alpha amino group. It's just that we have a secondary amine versus all the other ones are primary amines, just because proline likes to be different, right? And this introduces a lot of issues associated with things that we're going to talk about later on. But again, as always, we'll get to that when we get to that. Okay, pKa values of amino acids and side chains. I don't think you really have to memorize all of these values. You can just see that these are all roughly around 2. These are all roughly around 9. These pKa side chain values, it might be in your interest to memorize them, but I don't think you'll ever be asked direct questions on them. I think you'll always be able to figure it out based on a trend or based on the conceptual understanding that will obviously be required. But the more you have memorized, the more you have like, a thing to compare to if in case you've forgotten what the trend is, right? Like the more information knowledge you have, the easier it is to corroborate with other knowledge. Okay, so now we're going to go over a couple of lab techniques. So separation of amino acids. Electrophoresis is, probably something that you might have heard before if you've taken the 1L labs or, just generally intro biology. So we separate the amino acids based on their isoelectric point. So again, the isoelectric point is when the charge of the amino acid is 0, right? So let's take a look, right? So if the pH is equal to the pi, the amino acid is neutral. Perfect. If the pH is greater than the pi, the amino acid is negative, right? Because we have more A minus. If the pH is less than the pi, the amino acid is positive. We have more HA. So the greater the delta between pH and pI, the larger the difference in charge. So the whole point of isoelectric or like electrophoresis is to separate amino acids based on their pIs because at a given pH, they will have different charges, okay? And then we have a negative for the cathode, positive for the anode. Cathode, keep in mind, cathode means that we're attracting positives, which is why it's negatively charged, okay? This might be counterintuitive because you see cathode and you think, oh, positively charged. It must be attracting negatives. No, it's actually attracting positives. So just keep that in mind. The conventions are slightly different depending on what you've learned in the past. So this paper is in a buffered solution. This just means we have salt in the solution, basically something that can conduct electricity. So we have the charge across these. Yeah. Hydrogen is the thing that's actually used to visualize the location of amino acids after separation, because these amino acids don't look different, okay? They're just you can't see them without having some type of chemistry to visualize them. So we'll take a look at the chemistry associated with it later. It's not too terrible. It's just again one of those things that you should memorize and know the mechanisms of the individual steps in electrophoresis. But yeah, I'm just gonna do an overview of each of the techniques and then we'll get a little bit more into the specifics. Okay, paper chromatography. This is also known as TLC, thin layer chromatography. So we have a stationary phase, which is the medium used for separation, a mobile phase, the solvent that travels through the stationary phase. So the idea is that let's say we have a piece of paper. Okay, this is the stationary phase. Obviously, this is the stationary phase. Paper is not moving. Okay, I draw a line, and this is my baseline. Analyte is a mixture of the things that I'm trying to separate. Okay, so what's going to happen is I'm going to put them in a solution. Okay, and this solution is going to slowly travel up this line here, this paper here. Just because, I mean, if you've ever taken a piece of paper, you soaked it in water, like how it slowly travels up through capillary action, which is just a fancy way of saying like water will like slowly uh, go up a piece of paper, right? And we'll actually get separation based on polarity, okay? So earlier here, we had separation based on isoelectric point, based on charge. This is going to be separation based on polarity. So like we talked about earlier, like attracts like, non-like does not attract non-like. The stationary phase is polar, generally speaking, right? So the more polar molecule will be more tightly stuck to the stationary phase, which makes it harder to move across the phase, right? Which is why you see the polar solution, the polar amino acid, much lower than the less polar one, right? Because if we have a non-polar on a polar, like we're just gonna slide right over it, right? Um, but if we have polar on a polar, then we're going to experience a lot of different interaction forces between our mobile phase and the amino acids. Okay. And sometimes people bring up reverse chromatography, and all that is you make the mobile phase non-polar. By convention, it's polar. You make it non-polar. Wow, it reverses the trend. It's not that deep. TLC, paper chromatography, separates based on polarity. So side chain functional group and or size will determine the polarity, right? So side chain polarity, charged side chains are the most predominant. Hydrogen bond forming is next, small alkyl groups, and then large alkyl groups, right? So this is all to do with we'll get more attraction to the polar in this hierarchy. We also use anhydride to visualize the amino acids. Okay. Another technique we can use is ion exchange chromatography, which we are separating amino acids based on their pi. So the stationary phase, it's an example of chromatography where this phase, this piece of paper is an ionic resin, right? So if it's cation exchange resin, then we have a negatively charged stationary phase. So this paper is negatively charged, okay? And lysine will exchange. You don't have to really terribly understand the specifics associated with these counterions, ions. All you really have to understand is that in cationic exchange resin, the negative will move easily through the resin because cationic exchange resin means that we have negatively charged resin. And in anionic exchange resin, losses will move very easily because we have a positively charged resin. So again, keep in mind, cationic in this context means that because it's a cationic exchange resin, it's attracting cationic things, so it's negative. So this is so important because if you mix this up, you have the whole problem upside down. Um, cool. So this is a picture of electrophoresis. We have negative and positive, and we have our paper. We're going from one liquid base to another liquid. Okay, this is ninhydrins. So we start with the ninhydrin, which is the hydrate. It's just a glorified hydrate, right? So if we look at this point here, it's a tetrahedral intermediate, right? OH, OH, R group. Cool. And we turn it into a ketone with water. So all we're doing is we're collapsing this hydrate into a ketone, right? Cool. Then we add an amino acid. So it is a glorified imine formation, right? So we've seen this mechanism over and over. We know that the N will attach here and we'll lose two hydrogens. So after we do that, the negatives will come here. We'll actually decarboxylate, which is removing a CO2, which we also briefly saw at the end of last quarter. These electrons will move here, come here, kick us up here. Cool. Now we'll tautomerize. Why? Because we always tautomerize when it's possible, essentially. So these electrons will come down, we'll grab a hydrogen, kick it off. Cool. Great. Deaminated amino acid. Cool. So with this, what did we do here? Basically, all we did was we attached a conjugated system to our amino acid. So now it can fluoresce, right? So now we can actually visualize it and see what's going on, right? So we know that conjugation, like in aromatic systems, is how we get things to be visualized, right? In biological systems, when you're trying to track something, you often use an aromatic amino acid, often tryptophan, or tyrosine because those are conjugated so we can see them. That's all it is. Electrophoresis visualization. Okay, anode, cathode. Okay, so the more negative things will move to the anode, the more positive things will move to the cathode. The things that are relatively neutral will make not as much movement from the center, right? Make sense? Cool. And I guess the point of this is our unknown. Our unknown was just a mix of amino acids, right? So we see that our unknown split up into three different things from this dot, right? So this dot looks a lot like aspartate, right? So it's almost like we have a bunch of amino acids as like comparisons, right? And we know that aspartate will move roughly to here. We know glycine will move roughly to here. We know histidine will move roughly to here. we don't know what our amino acids are, right? But we compare them against where they move. So we'll see that the unknown contains aspartate. We'll see that this corresponds with the leucine. This corresponds with lysine. So it's probably what you've seen before. Running a gel, um, running electrophoresis. All these things are just, taking known things, seeing where they move, and comparing our unknown thing to it, and just matching things, right? So it's at the end of the day not terribly complicated, but it will take a little bit of practice to kind of get the hang of. Okay, paper thin layer chromatography, same concept. Ion exchange chromatography. So the idea of the resins is this is a cation exchange resin. These are counter ions. Na plus is just a counter ion, right? Like whenever you see NaNH2 or like NaH, sodium hydride, you never really care about Na, right? So it's just an ion that's kind of there for like the time being, right? But it's pretty okay on its own, right? NaCl greatly dissolves into salt like water, right? So anyway, it's just a intermediary bookkeeper. Cation exchange, lower pi elutes first, anion exchange, higher pi elutes first. That just has to do with positives and negatives, right? Okay. So now we're going to be moving on to a little bit of more like mechanistic things. So there are a couple of different ways to synthesize amino acids. I think we're going to go through three or four of them. I guess we're going to go through five of them. The first way to do it is HVZ, Hell, Voller, Zielinski. So we have three reagents. The first one is installing a BR that is ipso. Ipso means it's directly connected to this carbonyl. So what's going to happen is basically this reagent is pretty much the same thing as Sockle 2. So we recall that we learned about Sockle 2 last quarter to activate lower energy carboxylic acid derivatives. So the first step is installing a BR here. Then we're going to get this interesting tautomerization type thing. Um, so what's basically going to happen is we tautomerize and we have an H here, so a base will abstract an H from here. The electrons will go here, we'll kick up here, and now we have this structure. We have the enolate ion. And from the enolate ion, it comes down, we grab a Br, we kick off a Br, and now we're left with this dibrominated structure. Backside attack to kick off this Br, and we're left with an amino acid. Cool. Um, and I think that, 1,9B stressed mechanisms heavily, right? But I think in general, as long as you understand approximately what each reagent is doing, it should generally be sufficient for the purposes of this class, right? Like the bulk majority of your exams is not really going to be focusing heavily on mechanisms. Okay, reductive amination. This is just another way to synthesize amino acids. Excess NH3. The first thing we'll do is amine formation. It's also important, I think, to really understand the starting and ending and reagents, okay? So don't worry too much about the mechanisms they go through. Hopefully you should have some intuition from it, like, going through this material on your own by now. But just as long as you can remember the starting material, the reagents, and the end structure, I think that's not bad. And let's take a look at them though. Alpha keto acid. So this is just we have a carboxylic acid, alpha position, we have a carbonyl. Alpha keto acid. Cool. Excess NH3, trace acid. So this is amine formation, right? So we'll add the amine at here. We won't add the amine here, if you recall, because of esters are not of the same reactivity as just naked keto groups. So step two, H2 palladium on carbon will reduce this double bond NH into NH2. We could also use NaBH3CN, whatever reduces imines and enamines, I think. But H2 palladium and carbon is what's generally accepted, and what you should have memorized. Okay, N-pentada metamalonic ester synthesis. So this is Gabriel synthesis and malonic ester synthesis kind of mixed up, right? So we start with our phthalimide, which is basically just a nitrogen connected to a glorified withdrawn group dicarboxylic acid. We start with an alpha bromo malonic ester. Okay. So, you know, it might be hard to just memorize these off the bat if you didn't really understand the chemistry, but By understanding the chemistry, we know that like, okay, this spot is gonna be great for an enolate ion to form, right? Because it's super resonance stabilized. This is a pKa of like 11, I think. Um, so this, will attack here. It'll kick off this BR, and from there we'll get an enolate formation. So we'll move one of these symmetric, so it doesn't matter. We'll add the alkyl bromide, right? The R group that we want to install. Because remember, an amino acid is just of the structure of we have a carboxylic acid, we have a amino group that's alpha, and then we have this R group, right? So we attach the R group, hydrolysis removes all of the protecting stuff, and we decarboxylate just because, we started with two carboxylic acids, and an amino acid generally, guess what? Excuse me. So yeah, we'll end with an alpha amino acid. Okay. Again, it's good to have these initial structures memorized and the final thing and just have a general understanding of how things happen. But I wouldn't stress too heavily understanding every minute detail of mechanisms the same way that you had to in 109B. Okay. Acetaminophenolonic ester synthesis. Okay. So we start with the acetaminophenolonic ester. We get an enolate formed. We add the R group, hydrolysis to remove protecting stuff, and that's it. Cool. Strecker synthesis. I think this is the most useful method for synthesis, and it might become rather obvious later on why. Just that a lot of these synthesis methods have issues. Like for example, HPC can't be used to make amino acid with the carboxylic acid side, like in their side chain, and we could see how that would be the case, right? Because this whole like shtick of this reaction is we're transforming this carboxylic acid into like two places to install BRs, right? And then we replace one of the OHs with the BRs to restore the carboxylic acid, but then we add an amine here, right? And we only want to add one, right? We don't want to add a second one. If we had a carboxylic acid within the R group, we wouldn't be able to do it. So just keep in mind that understanding of the mechanisms, again, is not fully required, but it does help you differentiate between synthesis that you can and can't do, and which R group specifically you could or couldn't install using what particular method. Yeah. So let's go to Strecker synthesis, right? So we start with an aldehyde, excess NH3, trace acid to install the amino. Then we add a CN because we want to increase the carbon chain. We reduce the CN into a carboxylic acid, right? So all of these are mechanisms that you've seen before. So you might already remember them, or maybe you blurred 109B completely out of your mind. But either way, I think it's sufficient to just have a general understanding of what's going on in order to be a successful student in this course. Okay, cool. We just talked about those. Okay, kinetic resolution. So stereochemistry, we haven't really talked about so far, but stereochemistry is one of those things that always matters in a biological context, just because in biology, the context is so important, and 3D structures and enzymes and all these things are highly specifically designed for a particular 3D orientation. Um, so with kinetic resolution, let's see what's going on, right? So the methods that we talked about earlier made D and L amino acids, right? There was really no specificity. So what can we do? We start with our D and L amino acid mix and we add AC2O. After we do that, what we're doing is we're adding this group here, okay? Um, Pig kidney amino acylase in H2O is it's an enzyme, okay, which means it's stereospecific. So it'll only cleave this off of the L amino acid, okay? So that means that we're able to separate our amino acid really easily because this compound is very different than this compound. These two are very easy to separate, right? They're very chemically distinct versus this and it's an ant like this and it's an enantiomer. D and L are pretty, like similar, right? You can use something called chiral columns, and there are techniques, but using an enzyme is just much better. This is called kinetic resolution. This is a way to take a mix of D and L amino acids and just get L amino acids, or if you wanted, get D amino acids, and then there's probably specific chemistry that's used to remove a D amino acid from here, right? Okay, cool. Peptides and disulfide bonds. So a peptide bond is an amide bond between an alpha amine of an amino acid and the carboxylic acid of another, right? So this is the peptide bond. Basically, you have a nitrogen that is directly connected to the carbonyl, right? This one is not a peptide bond to this because we have it connected to the alpha carbon. This one is directly connected. So this is the peptide bond, right? Because peptide bonds have this resonance structure too, and it's, like I think it's kind of easy to remember, right? N terminus, left side, you always write from N terminus to C terminus. N, it's really easy. Nitrogen, N. C terminus, I don't know why it's called C terminus. Oh, because carboxylic acid, right? So carboxylic acid, C terminus, N to C. Okay. Always write the peptide from N to C. Glycine, arginine, histidine, ILE. Cool. Dashes equals the known sequence, commas equal unknown sequence, right? So if you're given glycine dash arginine dash histidine slash ILE, this is the order. If you were given a mix of these, you don't know the order. Okay. Peptide bond has partial double bond characteristic, making it rigid and planar, so there's no rotation about the peptide bond. What we'd expect, right? This is sp2 hybridized. At first, it doesn't look like it, but then when you take into account resonance, it is, right? Cool. Disulfide bonds. Cysteine can make disulfide bonds to create a disulfide bridge to cross-link portions of a polypeptide. We have some oxidizing agent. We can go from SH to SS. The mechanism is as follows. It's pretty standard stuff. Cool. We can also go backwards. We can reduce it into RSH. This is only formed by cysteine and not methionine. And it basically has to do with the fact that cysteine, the SH group, is a lot closer to all the action, so it has a lot more stability. And like we talked about earlier, the pKa's, the pH, it really matters based on the context of where it is in a molecule, right? Having an amino acid close to the carboxylic acid is very different than having an amino group super far away. Okay. Kinetic resolution, we talked about this earlier. Okay, peptide synthesis. So there's a lot of stuff going on with peptide synthesis, okay? So first we're going to talk about peptide synthesis using a non-automated method, and then we're going to talk about the automated solid field or solid state method, Merrifield synthesis method, okay? And it's pretty good to have a good understanding of both of these, all right? So let's get started, right? So if I wanted to attach valine to alanine, there's some issues that we run into, right? Because there's NHs here, there's O's here. What will attack what? How will we add? Right? So we need to protect the amine that is not attacking and activate the carboxylic acid that is being attacked. So this is where nitrogen protecting groups come in. BOC, TBOC is the most common thing that's used to protect things. So if we slow down, it's kind of easy to see why it's named di-tert-butyl dicarbonate, right? So dicarbonate, two carbonyls, well, tert-butyl, di-tert-butyl, two tert-butyl groups, well, it's also known as BOC anhydride or BOC2O, right? So you should be, pretty comfortable seeing it either as the actual structure or BOC. I don't think you ever really see di-tert-butyl dicarbonate written out, but I think if you're given the full name, it's a lot easier to reason through it than just being given BOC, right? Um, anyway, so these side chains are also in need of protecting groups, so we'll add a BOC here to protect this structure, and then we know exactly what to attack, right? Um, and then for this nitrogen, we can protect it here, BOC. Cool. So carboxylic acid activation is something called DCC. Um, I don't remember what DCC stands for, but we have a CN connected to cyclohexane, CN cyclohexane. I don't know, dicyanide cyclohexane maybe. Makes sense, right? Cyanide, cyclohexane. All these molecules have a lot of symmetry. All the molecules in this class in general will have a lot of symmetry. So if you can remember half of it, like you got the whole structure. Um, okay. So the whole point of this is to activate the amino acid, right? So we're making something more propense to nucleophilic attack. Peptide bond formation. Once we have the Bach protecting group and we have this amine, we attack here. Okay, and then we have a lot of different arrow pushing involved, but the general idea is that these come down and this kicks off this group, right? So N-Bach protected valine alanine. TFA is the thing that will remove the Bach protecting groups. So overarchingly speaking, Like once we have a Bach group added, we don't have to keep on adding Bach groups. Once we add it once, we just keep on like activating and adding. Okay, cool. So automated peptide synthesis. So the synthesis method described here, it does work, but there's just a lot of issues. It's a really bad yield. So people came up with this automated peptide synthesis method, the Merrifield technique, where you make peptides from the C terminus to the N terminus. These are some N protecting groups, and what they're used for, what we remove them with. I think generally you're on the hook for Bach and not really the rest of them. Sometimes FMOC, but Bach I would definitely make sure I understand. Okay, some other things to consider. These are all considerations we already talked about. Some amino acids have, side chains that have similar modes of reactivity to the side chains that we're working with. So we need to make sure those are protected. Cool. Okay, diminishing yields of peptide synthesis. If we assume each amino acid added to a growing chain was done with an 80% yield, we'd see the overall yields, right? 80 times 80 is 64. 64 times 80 is 51. 51. So the yields are really bad, right? If we wanted a chain of even like 10 amino acids, that's like, less than a 15% yield. Let's not even, consider having an amino acid of 20 or 30. That's a 1% yield or 0.15% yield. Um, anyway, so they needed to come up with this method of automated peptide synthesis. So the idea is you have this bead, and this bead is a solid support. So all the chemistry you're doing is attached to this solid support thing. And the big advantage of this is each step you can kind of wash away the impurities, and you can prevent a lot of side reactions from happening. So this is the accepted method for doing peptide synthesis. It works on very similar principles to what we just discussed. The main caveat to it is we have everything attached to a solid support. Um, cool. Um, yeah, I mean, the only thing to guys call out is the solid support is removed with hydrofluoric acid, HF, in the final step. Supports, protecting groups, all these things are always removed with some type of acid. Okay, so now we're going to talk about determining the primary structure of amino acids, right? So, given a peptide, how can we figure out the sequence of these peptides, right? So, let's look into it. So, the first step will be to break the disulfide bonds. Then we determine the number and type of amino acids in the protein. We can use Edmond degradation to find the N-terminal amino acid, use carboxypeptidase, A or B to find C-terminal amino acids. We can do partial hydrolysis, use endopeptidases, determine locations of disulfide bonds. Okay. So that's a lot. So let's break it down step by step. First of all, reducing disulfide bonds, right? So 2-mercaptoethanol is just the reagent that we use to break S's, generally speaking. So all it does is take these two groups that are attached and break them down. So we add an H on either side and we break this bond. Cool. Iodoacetic acid, this will add this structure. Um, Basically what's going to happen is the SR is going to be added to here in place of the iodine, right? So this will attack here, and we'll have SR carboxylic acid. This combining with this, get this. Cool. Hydrolysis. So protein 6 molar HCl at 100 degrees Celsius left for 24 hours will split up all the proteins into their individual amino acids. It's very important to note, though, that it doesn't necessarily split it up into the amino acids that were in the peptide. Okay. All the sparagenes and glutamines will be hydrolyzed to aspartates and glutamates. And it makes a lot of very good sense why this happens. If you compare their structures, you can see that, like at a certain pH, their structures are basically the same. Um, anyway, so this skews identification for those two amino acids. Tryptophan will also decompose in acidic conditions, so just something to make note of, right? Determining N-terminal amino acid with Edmond degradation. So we'll talk about it, I think, a little bit later. All you really need to know is like not a lot about the arrow pushing in organic chemistry, just that if we say that we use Edmond's reagent, what we're going to get is we're going to get Edmond's reagent plus a peptide. We're going to get PTH amino acid plus the shortened peptide. So basically, from this phthalimide, we'll be able to figure out what the amino acid was at the beginning, right? Determining C-terminal amino acid by carboxypeptidase. So this allows us to figure out the end amino acid. So carboxypeptidase A and B are both used for the same thing. They work for slightly different amino acids. A works on all the amino acids except arginine and lysine. which means that if you have a C-terminal amino acid and it's arginine plus lysine, you get no reaction. Um, so we have to use carboxypeptidase B to cleave off arginine and lysine. Cool. Partial hydrolysis. Okay. So partial hydrolysis is we have certain enzymes that are used to break apart amino acid chains at specific spots. This kind of is under the same category as endopeptidases. So, kind of the things you're going to be on the hook for is knowing which amino acids cleave what. Okay, so trypsin, chymotrypsin, elastase, thermolysine, and cyanogen bromide, they all cleave peptides at specific points. And based on these and the fragments, you're kind of expected to assemble the fragments together into their peptide structures. Okay, and it might make a little bit more sense when you're doing problems later on, but this is just kind of going to be a practice thing. You'll have to just do a couple problems to kind of get a hang of how we do these problems. But anyway, the important thing to call out here, I guess, is these are all enzymes. They all cleave on the C-terminal side. This is not an enzyme, which means it's unaffected by proline. What I mean by that is if proline is C-terminal to any of these, it will not cleave for enzymes specifically, because enzymes have a particular 3D orientation in this pocket that they have to bind in. So proline disrupts that. Um, so we'll get issues with those. And the issues with those are just, clever questions that professors can ask on texts, unfortunately. Cyanogen bromide cleaves the peptide, but it's not an enzyme, so it's not affected by proline. Protein structure, primary amino acid sequence. So secondary is repetitive conformations by interactions of the polypeptide protein backbone. Rigidity of peptide bonds limits possible conformations. We maximize the amount of hydrogen bonds. Side chains are spaced out to minimize steric interactions or repulsion of like charges. Tertiary has to do with overall 3D shape a protein adopts under folding. This is based on side chain interactions. So proteins fold spontaneously in solutions to maximize their stability. Destabilizing interactions can include, but aren't necessarily limited to disulfide bonds, hydrogen bonds, electrostatic attraction, and hydrophobic interactions. Cool. Quaternary is the arrangement of protein subunits, polypeptides with respect to each other. Okay. This is just what we talked about, right? Oh, so what we talked about. Okay. I'm pretty sure this is all of what we just covered. We didn't cover the specific organic chemistry of this. We can take a quick look here. The nitrogen will attack the carbon, double bond, we'll grab a hydrogen, kick off the B, and then we'll get a bunch of arrow pushing. And again, you can kind of follow the arrow pushing, and it would be helpful to know and understand this mechanism. But generally speaking, as long as you know the general idea and the starting and ending reagents, or the starting and ending compounds and the reagents involved, I think it's usually sufficient. You'll probably get like one question or two questions on mechanisms per examination. So this is not really like super high yield stuff, right? Carboxypeptidases, we already covered this. Partial hydrolysis. Okay, so I didn't really do a great job of explaining what was going on earlier, so maybe this visual will be a little bit better. Um, so when we get partial hydrolysis, we're cutting at different points, right? So we're having to assemble these fragments in a way that'll yield like our final compound. And the way that we figure that out is oftentimes with endopeptidases. So we know that it has to cleave at these points, these points, these points. So the question will basically be like, okay, like we use these endopeptidases and these are the chains of amino acids we got. And then you kind of have to assemble it together. It's really easy to find practice problems for this, and you'll probably go through them in class too. But this is kind of always a super high yield topic. So it's kind of good to practice with this. And I don't think I can really give too many tips on this. This is just one of the things that you have to practice. Cyanogen bromide. This is the reaction mechanism. I've never used this reaction mechanism, but something you're supposed to know, I guess. Okay, determining sulfur-sulfur bond location. Secondary structure. All right. I mean, you can pause the videos at these on these slides and read them out. I'm not going to go through them because I would just be reading out the verbatim slides, which I don't think is, terribly useful. I don't really see anything that's like super, jumping out at me to like call out. Yeah, I guess that wraps it up for amino acids. Again, this is a lot of content, and there's not that much conceptual backing to it. It just really comes down to like you have to memorize a lot of things, and you do have to practice this stuff so it really like sticks in your head, right? All right, I think that wraps it up though.